This is chapter 5.1a, interpretation of Z-transform. We'll discuss about interpretation of Z-transform from the perspective of polynomial as well as dot product. Let's recap. Given a sequence x of n, to convert it into the Z-transform, simply do this, and this will look like the equation on the right hand side. It basically converts this sequence into a polynomial with power z. Notice that the index of the original sequence becomes the power in the z, in this case the negative power of z. Hence, there is a one-to-one correspondence between the polynomial power and the original value, as well as the coefficient of the original sequence. Hence, this is a lossless transform. It simply converts a sequence into a polynomial. So this is the explanation that I have just offered. And we can see that for finite length x of n, the polynomial is of finite power and the conversion is trivial because we can simply identify the power as well as the coefficients of the original polynomial. However, when xn is infinite, then it is important to choose appropriate z such that the series, this is a series because this is an infinite sum, the series can converge. So the region of convergence becomes important. We have to select particular value of z such that the z-transform exists. So that was studied under the topic of region of convergence. We now offer the second interpretation, that of an inner product. The inner product is written in this form. X with a vector phi is represented as the elements of x as the first slot with the element of phi as the second slot, and because we are dealing with complex vectors, the second slot's entries are being conjugated. Let's deal with a finite number of elements first. This is the definition of a complex inner product between two vectors x and phi. When we interpret this equation, you can think of this equation as generating a number, because out will pop out a number, and this number is a complex number, and this complex number will reveal the magnitude and phase of how the vector x is related to the vector phi. By magnitude, we mean that we can use phi multiplied by a certain magnitude and adjust the phase of the complex vector to align it to the vector x, or to approximate x. In other words, we can interpret this inner product as how the x vector will be projected into phi, the space of phi, or how much of x can be represented by phi. If we see it from a linear algebra perspective, let u, the vector, be projected onto v. Let's assume v has norm 1. The projection of u onto v is this vector over here. It is a vector along v. The projection of u onto v is a vector along v. Its length is the inner product. If v, the length, is equals to 1. So you can now think of an inner product as how one vector is related to another vector in the vector's direction. This is a very interesting and important interpretation from the linear algebra's perspective, or vector space perspective. In terms of Z-transform, we think of projecting our signal of interest, which is x, into different sequences of phi. Let's now continue with the interpretation, and now we examine that this is phi. Oh, actually this is the conjugate of phi. Because remember that when we are dealing with complex vector, the second entry must be conjugated. Alright, let's expand xz in terms of the ZTransform equation. So this is z naught multiplied by x naught. This is x1 multiplied by z minus 1, x2 multiplied by z minus 2. X minus 1 multiplied by z plus 1. So this is a bilateral ZTransform. If we treat this as vectors, x would be a column vector of x minus 1, x0, x1, x2, and so on and so forth until x infinity. It is a column vector of the elements of x, with n equals to 0 being here. What about the corresponding complex conjugate of phi? On the right hand side, we show this vector as a column vector where we have elements of z to the power of n with a complex conjugate. The reason why we need the complex conjugate here now is that later on, when we apply it as a vector times vector notation, we will have to conjugate it again. So we must remove the conjugate later on. But in any case, this is the equation that is representing this summation. To save space, when we write the vector x in this way, we include the transpose here to write it as a row representation. The transpose will push the vector from a horizontal position into the vertical one. The phi is also with transpose. Its entries are complex conjugated, and later on, when we want to make it into a row vector, we need to perform something called conjugate transpose, meaning we transpose as well as conjugate each element. This is so that we can obtain phi hx to represent this equation over here. The take-home message is this: the inner product, which is this guy over here, is ultimately represented as this equation. We are projecting the sequence x into a sequence phi, where phi takes this form. And because we are dealing with complex vectors, the inner product in the second entry needs to be in its complex, or needs to be in its conjugate form. So you may now be wondering, what does this look like? What does this phi look like? Or what does this phi Hermitian look like? Let us now plot. Let us plot z plus n and z minus n for n equals to 0, 1, 2, 3, and so on. On this axis is the real axis. On this axis is the imaginary axis. This is the this is the time. This is the imaginary axis. So we have the real axis, the imaginary axis, as well as time going from 0 to 30 in this case. We begin with this equation 1.05 e to the power of j 0.25 pi n for n equals to 0, 1, 2, and so on. When we substitute n equals to 0, this number becomes e plus j0, which is 1. Therefore, the first number at z at time 0 is equals to 1.05. or the sequence Zn at time n equals to 0 is 1.05. Where is it? It is exactly at this point. This is the horizontal axis and it is at 1.05 with imaginary value 0. What happens at n equals to 1? At n equals to 1, then we are increasing by 0.25 pi in terms of the expression here. What is ej 0.25 pi times n equals to 1? This is cosine 0.25 pi plus j sine 0.25 pi. This whole expression is multiplied by 1.05 to the power of n equals to 1. And this is the second point. 1.05 n is to the power of 1 cosine 0.25 pi plus j sine 0.25 pi. I made a mistake just now. This value should be 1.00. The reason being that the original in this equation, the first element is 1.05 to the power of 0 cosine 0 plus j sine 0. Hence, this value 1.05 to the power of 0 is 1. And cosine 0 is 1 plus j 0. Hence, the final value is 1 plus j 0. You can then track the next equation or the next element. This is, for example, x2. This is x3. This is x4. And so on and so forth. The interpretation is that it is a complex exponential rotating in the direction clockwise direction, and it becomes bigger and bigger due to 1.05 to the power of n. That red line is drawn for you to see the link between all this circle, which is the only value we can see, as it is the value that occurs during integer values of time or sample index n. In conclusion, z to the power of positive n is a complex exponential rotating anti-clockwise, and it becomes bigger and bigger due to the growing 1.05 to the power of n. What about z to the power of minus n? Z to the power of minus n is equal to 1 over cn. So in fact, it is the reciprocal of this equation. So as this is becoming bigger and bigger as time increases, therefore this becomes smaller and smaller. Not only that, there is also a difference. Because it's 1 over z to the power of n, the angle will be negated. So this is a clockwise direction, while this is a anti-clockwise direction. So z to the power of minus n is a complex exponential that is decaying, and it is rotating anti-clockwise. Compared to, on the left, we have a complex exponential that is growing, and the complex exponential is rotating anti-clockwise. So you must understand these two sequences very well. Thank you.